Welcome to the next session. Now, in this session, we discuss classroom workbook followed by concept. The concept is we discuss double integrals, followed by line integrals. Now, let us start the session with the question number 72. Go through classroom workbook, question number 72. The value of k for which the vectors a bar equal to 2i bar minus 3j bar and b bar equal to ki bar plus 4j bar. The value of k such that the vectors a bar equal to this and b bar equal to this are orthogonal to each other is blank. So we need to find the value of k for which these two vectors are orthogonal. We say that two vectors are orthogonal if the angle between them is 90 degrees. Or simple words, just make the dot product equal to 0. When the dot product of two vectors is 0, then these vectors are orthogonal vectors. Find the dot product 2 into k, 2k minus 3 into 4. So this is 2k minus 12 equal to 0 implies k equal to 6. Note this point. The angle between the vectors, the angle between the vectors 2i bar minus j bar plus k bar and I bar plus j bar minus k bar is, options are given. So we need to find the angle between these two vectors. Assume that this vector is a bar and this vector is b bar. So let us apply the first formula. Cos theta is a bar dot b bar divided by norm a bar times norm b bar. Therefore, cos theta equal to the dot product 2 into 1, 2, minus 1 into plus 1, minus 1, 1 into minus 1, minus 1. Anyhow, this is 0, so I need not evaluate norm a bar times norm b bar. So, therefore, cos theta equal to 0. Therefore, theta is 90 degrees. So, here dot product is 0, so the angle between them is 90 degrees. Note this point. Now we start the concept of line integral. Very, very important concept. Suppose we have a vector f bar which is given by f1 I bar plus f2 j bar plus f3 k bar. So this is my general vector f bar. Suppose R is a standard position vector which is given by xi bar plus yj bar plus zk bar, and C is any curve. C is any curve. Any curve means it can be a square, normal it can be circle, or it can be a rectangle or a line joining of two three-dimensional points, etc. So this is my general vector f bar equal to this. This is a standard position vector R bar and C is any curve. Now these three quantities measure line integral, and this will be like this: integral f bar dot dr bar over C. This is the standard form of line integral. Integral f bar dot dr bar over C. This is my dot product. Integral f bar dot dr bar over C. Basically, this is nothing but line integral of f bar. This we can call it as the line integral of the vector f bar over the curve C. This is my general vector, standard position vector, and C is any curve. So in that case, integral f bar dot dr bar over C. This we can write it as integral f bar dot dr bar over C, and this is nothing but line integral of f bar over C. Okay, note this point. Let f bar equal to f1 I bar plus f2 j bar plus f3 k bar let f bar equal to f1 I bar plus f2 j bar plus f3 k bar be any vector and cb any curve then integral f bar dot dr bar over c, write c below integral f bar dot dr bar over c is called line integral of f bar over c, where r bar equal to xi bar plus yj bar plus zk bar, which is called a standard position vector, Hope you understand this. Now let us simplify this. After that we have some challenges how to find these line integrals. Okay, let us simplify this. So what is the general structure of line integral? This integral f bar dot dr bar over c. What is f bar? f1 I bar plus f2 j bar plus f3 k bar dot product dr bar means dx I bar plus dy j bar plus dz k bar over c. Now let us simplify this. This is a dot product, so therefore this is integral f1 dx plus f2 dy plus f3 dz over the curve c. Therefore integral f bar dot dr bar over c equal to this. Note these points. Now what is the drawback of this RHS integral? Let's see. Here we are integrating f1 with respect to x, integrating f2 with respect to y, integrating f3 with respect to z. If f1 is only a function in terms of x, if f2 is only a function in terms of y, if f3 is a function only in terms of z, then I can go for linear property for integrals. Split the integral. This integral becomes integral f1 dx over c plus integral f2 dy over c plus integral f3 dz over c. So when this can be applied, if f1 is expressed only in terms of x, f2 is expressed only in terms of y, f3 is expressed only in terms of z, that too the limits of x are constants, limits of y are constants, and limits of z are constants. So when you have these much flexibilities, then you can go for normal integration, but don't expect these many flexibilities in case of line integrals. Okay, so our challenge is how to handle these line integrals. Okay, now let us discuss 3 standard procedures to find line integrals. Next concept, procedure to find a line integral. Now let us see case 1. Suppose if the curve C is parameterized like this. If C is parameterized as x equal to f of t, comma y equal to g of t, comma z equal to h of t, and the limits of t are constant limits. Let me explain what is parameterization. I will start with simple example. Suppose I have a circle x square plus y square equal to a square. Now this is an equation of a circle. It involves 2 variables x and y. Handling 2 variables is not a simple issue when compared to handling single variable. Now I will tell you one point on this. Suppose if I take x equal to a cos t, y equal to a sin t, and the limits of t are 0 to 2 pi. So from first quadrant to last quadrant, 0 to 2 pi. So basically this is called parametric equations to represent a circle x square plus y square equal to a square. Now take x equal to a cos t, take y equal to a sin t, a square cos square t plus a square sin square t, you will get a square. Therefore, the point lie on this circle is, the point which is lying on this circle is a cos t comma a sin t, where t limits are 0 to 2 pi. So what is the advantage? X is expressed in terms of t, single variable. Y is expressed in terms of a single variable t, and in particular we got the constant limits for t. That is more advantage for us. Okay. All limits are expressed in terms of, all variables are expressed in terms of a functions of single variable t. This is one advantage. Another advantage is we got the constant limits for t. This is the most effective point in case of parameterization. So that's why we were saying like this: if c is parameterized like this, x is a function of t, y is a function of t, z is a function of t, and limits of t are constants a and b. Now in this case, when this happens, then integral f bar dr bar over c, integral f bar dot dr bar over c can be written as integral a to b f bar of r of t dot product r dash of t dt. So this is my line integral when c is parameterized like this. All variables x, y, z are expressed in terms of a single variable t, and the limits of t are constants. In that case, my line integral, integral f bar dot dr bar over c becomes like this, because there is no more x. X is in terms of t, y is expressed in terms of t, z is expressed in terms of t. What are limits of t? A to b. Therefore, all variables are converted to t. Therefore, we will do integration with respect to t. Of course, limits of t are a to b. This f bar is f bar of r of t only. So what is f bar of r of t? In the f bar, in the vector f bar, whenever x occurs, replace it by f of t. Wherever y is there, replace it by g of t. Wherever z occurs, replace it by h of t. So what is this f bar of r of t? This is nothing but f bar when x equal to this, y equal to this, and z equal to this. The same f bar we are using here. Now this is a dr bar. Dr means differentiation. So that means differentiate r. Differentiate r. You know what is r bar? R is basically standard position vector xi bar plus yj bar plus zk bar. Therefore r equal to what is x? X is f of t. So f of t I bar. Y is g of t. So g of t j bar. Z is h of t. So this is h of t k bar. Now differentiate r is expressed in terms of t. There are no more x, y, z. Everything is in terms of t. So differentiate r dash of t equal to f dash of t I bar plus g dash of t j bar plus h dash of t k bar. So they refer to normal derivatives. Normal derivatives. Therefore this line integral becomes this. So all variables are expressed in terms of t. So the limits of t are a to b. Since all variables are in terms of t, integrate this with respect to t. This f bar is f bar only. But what is the notation? Here we are using f bar of r of t. That is f bar of r of t is nothing but the vector f bar when x is replaced by this, y is replaced by this, and z is replaced by this. And here dr bar, that means differentiation. So therefore r dash of t means express r in terms of functions of t, f of t, g of t, and h of t. Differentiate, you will get f dash of t I bar plus g dash of t j bar plus h dash of t k bar. So this is a vector in terms of t. This is a vector in terms of t. Applied dot product. This is a vector. This is a vector in terms of t. Applied dot product. You get a scalar in terms of variable t. We get a scalar expression in terms of t. And then normal integration. Apply normal integration followed by the limits a and b. Okay. This is very important case. Okay. Right. Case 1. First you write the heading, procedure to find a line integral. Procedure to find a line integral. Case 1. if C is parameterized as x equal to f of t, comma y equal to g of t, and z equal to h of t. X equal to f of t, y equal to g of t, z equal to h of t, and a less than or equal to t less than or equal to b, and a less than or equal to t less than or equal to b. Then write this: integral f bar dot dr bar over c, integral f bar dot dr bar over c equal to integral a to b f bar of r of t, integral a to b f bar of r of t dot r dash of t dt, dot r dash of t dt. Highlight this point, where f bar of r of t is nothing but, where f bar of r of t is nothing but the vector f bar of r of t is nothing but the vector f bar when x equal to f of t, comma y equal to g of t, and z equal to h of t. And r dash of t is obtained as follows, and r dash of t is obtained as follows. Write these three lines. Let's write one example, just parametric equations of a circle. Example, we were not finding a line integral, we were going for parametric equations of a circle. The parametric equations of a circle, x square plus y square equal to a square. The parametric equations of a circle, x square plus y square equal to a square, are x equal to a cos t, comma y equal to a sin t, and 0 less than or equal to t less than or equal to 2 pi, and 0 less than or equal to t less than or equal to 2 pi. This is the most effective case, right? Now we discuss second procedure. Suppose I have a line integral like this, integral p dx plus q dy over c. That means in the original line integral, I have taken f1 equal to p, f2 equal to q, and f3 is 0. So we have seen general structure of line integral. Integral f bar dot dr bar over c is integral f1 dx plus f2 dy plus f3 dz. So here we were taking a line integral in the xy plane only. There is no z coordinate. That means f1 is p, f2 is q, but f3 is 0. That means we were finding a line integral in xy plane only. So when you are measuring this line integral, that is integral p dx plus q dy over c, find the partial derivatives of this and this. So this line integral becomes a double integral dou q by dou x minus dou p by dou y dx dy over c. So a line integral becomes a double integral by finding partial derivatives. You can easily remember, here we are integrating p with respect to x. So differentiate p with respect to opposite variable. Here we are integrating q with respect to y. So differentiate q with respect to opposite variable x. So therefore integral p dx plus q dy over c equal to double integral dou q by dou x minus dou p by dou y dx dy over c if c is moving along anti-clock direction. If c is moving along anti-clock direction, because here curves move, one direction is anti-clock, another one is clockwise. If the direction of a curve is not specified, the default direction is anti-clockwise direction. So basically this result is called Green's theorem. This is called Green's theorem. So Green's theorem connects a line integral and a double integral. So write case 2 by putting the heading Green's theorem. So this is the statement of Green's theorem if C is moving along anti-clock direction. Note this. Suppose in the examination if they ask you the direction of C is clockwise direction, so multiply this value with minus sign. The default direction is anti-clockwise. If the direction is not mentioned, you take it anti-clock. So that means you do the original calculation. If they give you clockwise direction, simplify this value and take minus sign extra, right? Next, method 3. The name of method 3 is fundamental theorem of line integrals. Fundamental theorem on line integrals. Suppose we need to find integral f bar dot dr bar over C. I need to find this. This is my task. Integral f bar dot dr bar over C. Now if you want to measure this line integral, make sure about this curve C. Suppose if C is a line joining of 2 points. If C is a line joining of 2 points, call them as P1, A1, B1, C1 and P2, A2, B2, C2. That means the curve C is a line joining of two three-dimensional points. Be careful about this theorem. This is perfectly valid only for line joining of two 3D points, not for 2D. So when C is a line joining of two three-dimensional points and called f bar equal to null vector. So under two assumptions, we can get this line integral very easily. When you are finding this line integral, look at this curve C. If C is a line joining of 2 points P1 and P2, immediately evaluate curl of this vector. If curl of this vector equal to null vector, then what we know is this f bar must be equal to gradient of some scalar pi. Therefore, this pi is useful for me to get this line integral, and this line integral will be equal to pi of P2 minus pi of P1. So this is the statement of fundamental theorem on line integrals. There are two issues, basic issues. When you are measuring line integral, make sure about the curve C. If C is a line joining of two 3D points P1, A1, B1, C1 and P2, A2, B2, C2, immediately try to find curl of this vector. If curl of this vector is null vector, then we know that when curl is null vector, this f bar must be equal to gradient of some scalar. So here pi is a function in terms of x, y, z. So once you get pi value, this line integral becomes pi of second point minus pi of P1. This is a scalar in the variables x, y, z. So replace x, y, z by A2, B2, C2. In case of pi of P1, replace x, y, z by A1, B1, C1. Now my task is how to get pi. Let us see how to get this pi value. Here what is my f bar? F bar equal to grad pi. So what is f bar? F bar is f1 I bar plus f2 z bar plus f3 k bar. So this is equal to grad pi means dou pi by dou x I bar plus dou pi by dou y z bar plus dou pi by dou z k bar. Now equate this, you will get three equations. Dou pi by dou x equal to f1, dou pi by dou y equal to f2 and dou pi by dou y equal to f3. So sorry, dou pi by dou z equal to f3. Now let us take these three equations. Dou pi by dou x equal to f1, dou pi by dou y equal to f2, dou pi by dou z equal to f3. Solve for pi in terms of x, y, z. Once you get pi value, this line integral becomes pi of second point P2 minus pi of first point, that is P1. Okay. So when C is a line joining of 2 points and called f bar equal to null vector, my job will be very simple. Okay. My task will be very simple. This line integral becomes pi of second point minus pi of P1. Only thing is you need to find pi value. How to get pi? Since called f bar equal to null vector, then f bar must be equal to gradient of pi. So this is my f bar, general vector. Grad pi is this. So compare these two vectors, we can establish three equations. Dou pi by dou x equal to f1, dou pi by dou y equal to f2, dou pi by dou z equal to f3. Solve these three equations, you will get pi value. Once you get, my line integral becomes this. Okay. Now my question to all of you is C is a line joining of 2 points, but call is not a null vector. Then you need to go for alternative procedure, that is by using parameterization, or depends on status of the problem. Okay, we think about later, but for the time being, make sure about these 2 points. Write this point. Procedure 3, method 3, heading fundamental theorem on line integrals. Fundamental theorem on line integrals. Directly you can write this statement. Integral f bar dot dr bar over c equal to pi of p2 minus pi of p1. Highlight this if c is a line joining like this and followed by these steps. So continue all these points. This followed by these three equations. Now let us discuss double integrals. Suppose I have a double integral I equal to integral x1 to x2, integral y1 to y2, f of x comma y dx dy. Suppose my line double integral structure is like this. Double integral x1 to x2, integral y1 to y2, f of x comma y dx dy. Here x is changing from x1 to x2, y is changing from y1 to y2. Here the function contains two variables. If a function contains single variable, finding integration is very simple. Here the challenging task is how to handle double integrals. That means, so what does it mean is, with respect to which variable I need to integrate first. So order is an important issue. Let us see. In case of this double integral, x varies from x1 to x2 and y varies from y1 to y2. Now we have three different cases to find this double integral. Case 1 is this. Suppose if x1 comma x2 comma y1 comma y2 are constants. x1 comma x2 comma y1 comma y2 are constants. Then integrate f with respect to x first. Integrate f with respect to x first, followed by y, or vice versa. Vice versa means you can change order of integration. So if all the limits are constants, then no matter with respect to which variable you are doing integration, you can do integration with respect to x first followed by y, or with respect to y first followed by x. Therefore in that case my integral become like this. This I equal to integral x1 to x2, integral y1 to y2, f of x comma y dy followed by dx. Or this will be equivalent to integral y1 to y2, integral x1 to x2, f of x comma y dx followed by dy. So when you look at this, here parenthesis is given. Here the parenthesis is given to this at first. Sorry, this is given like this. So here parenthesis is given to with respect to y. That means you do integration with respect to y first followed by x, or do integration with respect to x first followed by y. But when you are integrating this, when you are finding this integral with respect to y, treat x as constant. When you are finding integral with respect to x, you treat y as constant. Therefore, when all the limits are constants, it doesn't matter with respect to which variable you are integrating at first. With respect to x first followed by y, or with respect to y first followed by x. Okay. So write this. Consider a double integral I equal to x1 to x2 integral x1 to x2 integral y1 to y2 f of x comma y dx dy, f of x comma y dx dy, where x varies from x1 to x2, and y varies from y1 to y2, Case 1. Note these points. Now let us discuss case 2. Suppose if x limits are constants, that is x1 comma x2 are constants and y1 comma y2 are functions of x. y1 comma y2 are functions of x only. I write it once again. If x1 comma x2 are constants and y1 comma y2 are functions of x only, then in this case we have only one sequence. That means integrate f with respect to y first followed by x. So here we don't have vice versa case, only single chance. X limits are constants but y limits are functions of x. That means y limits are frequently changing. Therefore, for safety measurement, integrate f with respect to y first. So therefore, in this case, we have only one chance. That means the value of I becomes this. So integrate f with respect to y first, followed by x only. Because x limits are constants, they do not affect integral value. But when limits are changing frequently, when you do integration later, so it might cause some dangerous effects. Okay. So therefore, when you are finding double integral, if y limits are functions of x and x limits are constants, then integrate f with respect to y first followed by x. Therefore, in that case, this double integral I becomes this. Note this point. Case 3. If x1, y1 comma y2 are constants, that is y limits are constants and x1 comma x2 are functions of y, and x1 comma x2 are functions of y only. So here in this case x limits are variables, so priority is given to variable x at first. So integrate f with respect to x first followed by y. In this case my integral becomes this. I equal to integral y1 to y2 integral x1 to x2 f of x comma y dx followed by dy. So just opposite to previous case. In the previously y limits are functions of x, x limits are constants. So integrate f with respect to y first followed by x. Now it is reverse. Y limits are constants but x limits are functions of y. That means x limits are variable limits. So integrate f with respect to x first. Variable limits have been given higher priority and then do integration with respect to y. Write this case 3.